everybody, it's Mrs. Hofferberth. Let's talk about photoelectron spectroscopy. Photoelectron spectroscopy, or PES, provides us information about how electrons are arranged in an atom. Up to this point, we've talked about the fact that we have a nucleus that contains protons and neutrons, and that the electrons are on the outside of the atom, and that there's a bunch of empty space in the atom, and the electrons are kind of floating around in that outside empty space. But we don't really know any details about how these atoms are actually arranged, and that's where PES is going to come in. So real quick, how photoelectron spectroscopy works. We take X-rays and we shine X-rays on the atom. And those X-rays cause electrons to be pulled out or ejected from the atom. And we measure the amount of energy it takes to eject those individual electrons. We're not going to go into a lot of the detail right now. If you're curious, come take Chem with me or ask me in class. I'm happy to talk about it. But that's not our priority for us today. We're going to be focusing more on what information we can gain from this photoelectron spectroscopy. To figure out what information we actually can get from it, we need to take a look at what a photoelectron spectrum looks like. And so here's what one looks like. You can see that we have a graph, and on the x-axis we have binding energy. Now, the binding energy is the amount of energy it takes to remove an electron from that atom. And you'll notice if you look at the x-axis, it's kind of backward from the way we usually see our axes. In this case, the large numbers are on the left and the small numbers are on the right. And so just be aware of that. And this energy is being measured in megajoules per mole of electrons. So how much energy it takes to remove those electrons. More energy on the left, less energy on the right. And then on the y-axis, we have signal strength, which equates to the number of electrons we have per atom. And so as I look at this data, I can see a couple of things. First off, I can figure out the total number of electrons that are in this atom. And since I know the total number of electrons and we're working with neutral atoms, the number of electrons has to be equal to the number of protons. So I know how many protons there are and therefore which element this is. In this case, if you look at the photoelectron spectrum, you have 2 electrons in the first peak, 2 electrons in the second, and 6 in the third. That's a total of 10 electrons. And 10 electrons is the element neon. So this is neon with its 10 electrons, and therefore it's 10 protons. So that's the first thing we know. The second thing we know is how those electrons are grouped together. We can see that the electrons are grouped into 3 groups. There are 2 electrons with a high binding energy, 2 electrons with a lower binding energy, there's a big gap there, and then 6 electrons with a slightly lower binding energy than those last 2. So what might cause different electrons to have different binding energies? Binding energy is about the amount of energy it takes to remove an electron. Well, what's holding an electron to an atom in the first place? It's the attraction between the positive nucleus with the protons in the nucleus and the negative electrons. So the greater that attractive force, the greater the binding energy is going to be, the harder it will be to remove those electrons. For a particular atom, the number of protons will stay the same for that particular element, for that particular atom. So it has to be something about the electrons that are changing. Well, the closer those electrons are to the nucleus, the greater the attractive force is going to be, and so the larger the binding energy. So we actually know that the electrons with the larger binding energy are closer to the nucleus, and the electrons that are at a lower binding energy are farther away from that nucleus. So we actually give information about where we find these electrons. It is worth noting that as you have more protons in an atom, the binding energy will increase just because there's more positive charge attracting those electrons. And so that's something we'll see as we look from atom to atom. But within a single atom for a particular element, what we see reflected in our binding energy is about spacing. So now that we see that we have a total of 10 electrons, so we know we've got 10 protons, they're grouped into 2 close to the nucleus, a big space, 2 farther from the nucleus, and then 6 just a little farther than that. we can actually draw like a sketch to represent what's going on here. This is totally not exactly reality, but we're just going to sketch this to try to get the gist of what we're talking about here. So I have 10 protons in the nucleus, and so I'm going to put those kind of at the center of the picture I'm going to draw. And then close to the nucleus, I have 2 electrons. And farther away from the nucleus, I have 2 more electrons. I'm going to change color and make these guys orange. I'm trying to have these be roughly evenly equidistant from that nucleus. And then, farthest yet from the nucleus, I have 6 more electrons. These guys, we're going to make these, okay, we're going to make these guys our green ones. And these are just a little farther than the orange ones, but there's 6 of them. 1, 2, 3, 4, 5, 6. There we go. So you see that we have 2 electrons really close, we've got a gap, and then we've got 2 electrons that are farther away, and then 6 electrons that are just a little bit farther away than that. So this collection of organization we refer to as the shell model. And what that means is that my electrons are being organized into shells. The electrons that are closest to the nucleus, here, this would be our inner shell. And then the electrons that are farther from the nucleus, these are going to be an outer shell. And within that outer shell, I have 2 different subshells, 2 different groups of electrons. So I have one subshell that is on average a little bit closer to the nucleus, it's more attracted to the nucleus, and I have a second subshell. So really, there's a lot of information that I have just from this one graph. So let's take a look at a second one. Okay, here we go, second photoelectron spectrum. Again, I see 3 peaks, so I know my electrons are grouped into 3 different categories, and there's a total of 1, 2, 3, 4, 5, 6, 7, 8. There's a total of 8 electrons, which means I will have 8 protons. If you look at a periodic table, this is oxygen. Okay, next thing to notice, if you look, all the peaks are just a little bit farther to the right. That's because there's fewer protons attracting the electrons to the nucleus, so everything has a slightly lower binding energy. But I still see my grouping and my categorization of where those electrons are found into the different shells. Again, I have my 8 protons in the middle, and then I have 2 electrons that are very close, so I'll try to draw them close and equidistant from that center nucleus. And then I have 2 electrons that are farther out. And then in this case, I have 4 electrons that are just a little farther. 1, 2, 3, 4. So we've got these electrons and we can tell where they're spaced out. This idea of trying to keep track of where electrons are relative to one another is why we often see the orbits being drawn to try to show that these 2 electrons are the same distance from that nucleus, that these 2 electrons are far away, and they could, we don't know where they are relative to the center, and then that these 4 electrons are a little bit farther away from the nucleus. And when you draw it this way, you can see the different shells. You can see the blue inner shell and then a gap, and then the orange and the green, as I have them drawn, representing the outer shell of electrons. I need to emphasize a couple of things. First off, this drawing, this sketch, is conveying particular pieces of information that we want. Information about the relative distance of electrons to the nucleus. It is in no way a perfectly accurate representation of an atom. The electrons do not exist in nice, cute little circles. The electrons are actually really, even the first electrons are really far away from the nucleus. There's tons of empty space, but I only have a small space to draw in. And so just recognize that these drawings are creating an image that's useful to gain insight about our atom. It's not that everything about them is right, but it does tell us information about the relative spacing of those electrons. And that that is accurate. It reflects the data that we see and helps us learn more about our atoms. So even though the whole picture is not correct, it's getting us one step closer to understanding what an atom looks like.